So in today's video, we're going to take a look at how we can determine the intervals over which a function is increasing or decreasing using differential calculus. And so essentially, we know that the derivative is defined as the slope of the tangent line of the function at a given point. Or another way to think about it is kind of the instantaneous rate of change of the function. And so with that in mind, if the rate of change is positive, so if f prime of x is positive, for x is a member of I, and I is just some sort of interval of the real number line. So if f prime of x is positive over this interval, it means that f is increasing for x is a member of I, right? And I is just a fancy way of writing a particular interval. I could have written, a, b, or whatever. However, if the derivative is negative, if f prime of x is less than 0 for x is a member of I, then this tells us that f is decreasing over this interval, right? So if the derivative is positive, it means that the rate of change is positive, so we're going to be increasing. If you want to think of it kind of graphically, the slope of the tangent line is positive, and the only way for that to hold is for the function to be increasing. Meanwhile, if the slope of the tangent line is negative, then the only way for that to hold is for the function to be decreasing. And if f prime of x is equal to 0, and this obviously has to be at a particular point, x equals a, we can say, then that tells us that f is stationary at x equals a, and we would refer to this particular point as a stationary point. Stationary point. And it's actually crucial that I make a small correction from the previous video where we talked about critical points. A critical point is a point at which the derivative is either 0 or undefined. So if f prime of x is equal to 0 or undefined, then this is what we would refer to as a critical point. But in general, if f prime of x is equal to 0, we can also state that it's a stationary point. If it's equal to 0, if it's undefined, then we can say that it's a critical point. But anyways, what we're going to do now is we're going to actually go ahead and try to analyze this function over here. So here we have f of x equals this very intense polynomial function that I don't really feel like going through. And essentially what we're going to do is we're going to try to find the intervals over which this function is increasing or decreasing. And we're going to actually see how we would approach these kind of problems using a number line. It's actually surprisingly helpful. So let's go ahead and delve into this. So first of all, we need to determine what the derivative of this function is, right? So we need to find f prime of x before we can even see where the derivative is positive and negative. So f prime of x, if we're to use the power rule over here, will be what? 3x squared plus 3x minus 6, right? And if you don't know how we got that, I encourage you to review the power rule videos that I made quite a while ago in differential calculus playlist. And so essentially now what we need to do is we just need to find intervals over which this is going to be negative. And so first of all, it may be a little bit easier if we actually factor this. So this is going to be equal to what we can factor out of 3. So it'll be 3 into x squared plus x minus 2, which is going to be equal to what? 3 times x minus 1 times x plus 2. Did I do that right? Negative 1 plus 2 is positive 1. Yep, okay. So now we have it in factored form, and we can already kind of from this determine what the stationary points are. So here we're going to have stationary points. So stationary points at x equals 1 and x equals negative 2. Right? And so let's actually go ahead and put this on a number line, and I'm going to show you why we're doing that in a moment. And maybe I'll change colors because why not? This is a nice light purple kind of color. Okay, so this is our number line right over here. Is that a straight line? Yeah. And so I'm going to actually go ahead and mark our stationary points on this number line. So here we have negative 2, here we have positive 1. So these are our two stationary points. And we know that if a function is going to change from positive to negative, then it has to kind of intersect the x-axis in order to become positive or negative. So in order to switch from either being positive or being negative, to either switch from positive to negative or negative to positive, we have to cross the x-axis. And so we know that until we cross the x-axis, we're going to be either positive for that entire interval or negative for that entire interval. Like we're not going to change without actually hitting the x-axis. And so with that in mind, we can just think of any arbitrary point within this interval right over here from negative infinity to negative 2. So let me actually go ahead and write that down. So from negative infinity to negative 2, we can pick any point within this interval, and that will tell us whether or not f prime is going to be positive. So Let me actually show you what I mean by that. So let's say we pick, for example, x equals -3. Suppose, why not? Because that's just located within our interval. And if we were to input that into f prime of x, so f prime of -3, that's going to be equal to 3 times -3 minus 1, which is -4, times -3 plus 2, which is -1, and this is going to end up being positive 12. So this is going to be a positive number. And so we know that over this interval, f prime of x is going to be greater than 0, right? Because if we pick any point and it's positive within that interval, then we know that it's going to be positive for the entire interval until we reach our endpoint. And so with that in mind, we can tell that our function is going to be increasing over this interval. So this tells us that f is, and you can usually denote this by an arrow, over, the interval x is a member of -∞ to -2, right? And we use that arrow to indicate that we're increasing, otherwise we'd use a downwards arrow. So we have that in mind, and sometimes what I like to do is put kind of a plus sign over our interval to indicate that we're increasing or that our first derivative is positive. And then we can take a look at the interval from -2 to +1, right? And so over here, we can pick any arbitrary value. The easiest one is probably just 0, right? So we can take f prime of 0, because 0 is contained within our interval, and we'll end up with 3 times -1 times +2. +2, I know I wrote a negative there. And that's going to be, what, -6? And so we know that over this interval, f prime of x is going to be less than 0, right? Because we picked one point, and because of the fact that it must be either positive over the interval or negative over the whole interval, and at one particular point that we selected it was negative, that tells us over the entire interval we're going to be negative, and that f is decreasing over the interval from x, for x is a member of -2 to +1. And then finally, the last thing we can check, and we can put a negative sign up here if you'd like, the last thing we need to check is just from 1 to +∞, and again, we can pick any arbitrary point. Maybe 2 would be a nice number. So f prime of 2, which is going to be 3 times, 3 times 2 minus 1, which is 1, times 2 plus 2, which is 4, so this is going to be equal to positive 12 again. And here we see that f prime of x is now greater than 0, which tells us that f is increasing over the interval from x is a member of 1 to infinity. So we're increasing when x is either from -∞ to -2 or from 1 to +∞, but within the interval -2 to 1, this open interval, we're going to be decreasing, and we're able to determine that without even graphing this function. All that we have to do is think about the first derivative and think about the intervals over which the first derivative is positive and or negative, and I can go ahead and put a plus sign over here to indicate that. So always use a number line, because it's very helpful to kind of visualize that, even if it's in a very simple way, in order to actually understand what's really going on.